Okay, before we get into atomic models and atomic spectra and how light can interact with atoms and actually cause changes in the energy levels that electrons are at, I did want to point out from the last video, I did get cut off right before I got a chance to write at the end. We've been talking about wave-particle duality, that light has behaviors of both waves and particles. All I wanted to write in those blanks is that I was giving the example of sometimes particles act like waves. Electrons exhibit an interference pattern. Atoms, molecules, protons, neutrons, even viruses, I've heard, can exhibit an interference pattern. So there's this idea that sometimes particles act like waves, and it turns out that everything in existence has both the properties of waves and particles. And that's a very, very interesting result that I don't think anyone would have predicted. Okay. So that's enough on wave-particle duality. We're going to talk about atomic models now. This is really the only place where there's any, I guess I want to say substantial math. Not in this first page. We're going to do a little history lesson first. But as we get into atomic models and atomic spectra, you'll see what I mean. It's not hard math at all. It's just where the most math is going to come in. So let's talk real quick about the history of the different models of matter and the atom that people have come up with in the past. So many people throughout history have tried to predict how what the smallest level of matter is. And the one I want to talk about first is Democritus. He was an ancient Greek in about 400 BC. He was the first person that I know of to really conceive of and write down his thoughts about matter and the smallest bits of matter. Atoms. Matter of fact, the word atom, I believe, comes from a Greek word that means indivisible. So we're going to skip forward about, more or less 2,000 years, a little bit more than 2,000 years, and we're going to get to J.J. Thomson. I believe he was a British guy. And J.J. Thomson is famous because he discovered that electrons, we knew kind of what electrons were at this point, but he was the first one to So I guess he really came up with a couple of the defining qualities of an electron. He discovered them to be extremely low mass, and he also discovered them to be negatively charged. Okay? And everyone knew at this point that atoms, the things that electrons were in, were neutral. Well, if the electron itself is negative, but the atom is neutral, he knew that there must be some positive charges somewhere in that atom as well. And Mr. Thomson, J.J. Thomson, his idea, and I don't know if he had like anything to base this off of, or if he was just kind of guessing. I'm sure he had something to base it off of. His idea was that the electrons were just embedded. So we had little negative charges embedded in a sort of like positive goo. That is spread throughout the atom. So kind of like what everyone always calls this is the plum pudding model. Plum pudding is, I believe, in a British dessert of some sort, and he imagined that raisins were just kind of like, or the electrons were kind of like raisins spread throughout a plum pudding. The plum pudding is this like amorphous, gooey substance that has a generic positive charge, and the electrons are like little raisins, or you could think of like chocolate chips, little chocolate chips like embedded inside, and they are negative. I guess an example I would think of is if you get like a yogurt cup from the supermarket and they've got the little chunks of fruit inside it. Imagine the little chunks of fruit are electrons, and the yogurt itself, the goo part, is positive. That was the Thomson model. So we have raisins in plum pudding. Okay, so there's our positive goo. And all these E's are just the little negative electrons. That was Thomson's model. But the nice thing about models is that you don't have to just accept that they're true. You can experiment and see if they're correct or not. So along comes Ernest Rutherford. I believe he was from New Zealand. And I think Rutherford, I could be getting it totally wrong. I think Rutherford was the guy, I think he was the guy where whenever he went into a lab, something automatically broke, which makes me very sympathetic to him. I could be getting my people mixed up. Yeah, I'm probably getting my people mixed up. Either way. Yeah, I'm definitely getting my people mixed up. Either way, Rutherford, very famous for what is known as the gold foil experiment. This was a test to see if Thomson's model of the electron was right. And what he did in the gold foil experiment, you probably talked about it in chemistry very briefly, is Rutherford devised a system where he was able to shoot positive helium nuclei. By the way, a helium nucleus, helium is the second element, so that means that it has 2 protons and 2 neutrons. And because it has 2 protons and 2 neutrons, we actually gave it a name. This is known as an alpha particle, which you probably also remember from chemistry. So he took positive helium nuclei, or essentially alpha particles, and he shot them at very high speed at gold foil. If Thomson was right, then the prediction was that the alpha particles should go straight through. If the positive goo model was really what was actually happening, there shouldn't be enough positive charge in any one area to deflect the alpha particles. Since it's very spread out, it shouldn't deflect it that much. It shouldn't impede the positive, it shouldn't impede the alpha particles at all. It should just go straight through without any real deviation. And this is why it's important to always follow an experiment through and do something many, many times. Because most of the time, those particles went straight through. Okay? But some of them got deflected back to weird angles. And some of them, in fact, bounced straight back, or almost straight back. And they were as if they were repelled by some dense positive charge. That was the only explanation. The only explanation was that if these particles are somehow getting deflected, in some cases straight back, well, they must be hitting some other positive charge that's very strong and pushing them back. So that was the only thing that they could think of. Okay, there must be some dense positive charge. It's not spread out throughout the atom. There must be some dense positive charge, probably in the middle. And what we eventually realized was that this must be evidence of a very small positive nucleus. Right in the center, with electrons in orbit around it. Okay? That was what this model advocated for. The only problem with this was that the orbits would inherently be unstable. And they would decay toward the nucleus. In other words, the electrons couldn't stay out there. Okay? The electrons couldn't stay out there for some reason. The orbits would eventually break down, the electrons would get pulled in towards the nucleus. But we knew the electrons weren't at the location of the nucleus. We knew that. We knew that they weren't. So there's some problems with this model, but it's a big step forward. Also in this model, you should have something where electrons should continuously emit light, which was not observed. And the reason that this must be the case is because, you remember how we said to create a light wave, you take an electron, and essentially you shake it back and forth, you accelerate it? Well, if you have electrons that are moving around in a circle, they always have centripetal acceleration. So shouldn't they always be emitting light? And we found that that's not the case. So we did learn some things from Rutherford's model. We know that there's a very dense small nucleus, but that doesn't help us because there are still problems with this model. So along comes Niels Bohr. Danish, I believe. Or no, Danish? No, Dutch? I think he's Danish. Okay, and Niels Bohr did some reading with some other guys. He took the idea of quantum theory from our friend Max Planck. Quantum theory was the idea that electrons can only gain or lose energy in fixed amounts. And we called these fixed amounts photons. You know photons as light particles. Okay? That's what a photon is. It's a particle of light. Electrons can only have, according to Bohr, certain fixed orbits. They can't go anywhere. There are certain orbits that seem to just work, that an electron is allowed to be in. I won't get into why those orbits are allowed. It's a little bit above what we need to do. But there are just, it's not that an electron can be anywhere around an atom. It has to be in a certain orbital location. It has to be a certain distance away from the nucleus. And what Bohr found was that electrons will go to higher orbits, or, as you guys might have learned last year, more energetic energy levels when they absorb a photon. They don't stay up there. They then fall back down and they emit a photon. And this photon appears to us as different types of light. And we called this lowest orbit, the orbit that is closest to the nucleus, we refer to that as the ground state. Okay, the lowest state. And on your reference tables, we're on page 3, this diagram right here. Okay, the ground state is here, closest to the nucleus. For a hydrogen atom, you've got two, essentially you've got two energy level diagrams to look at. One is the energy level diagram for a hydrogen atom, the other is some energy levels for a mercury atom. For hydrogen, the ground state is called N equals 1. For mercury, it's called A. Why do they call it N equals 1? Why do they call it A? I don't know. I don't care. It doesn't really matter, just as long as you know what the ground state is. Any sort of higher orbit other than the ground state, those are known as excited states. N equals 2, 3, 4, ... or B, C, D, ... So, electrons move up and down through the energy levels based on if they absorb or emit a photon. Okay? They move up and down through these certain fixed orbits. They can't just go anywhere. They have to be in these certain orbits that just work. If you give enough energy to an electron, it will escape. As a matter of fact, if you look at the energy levels, you'll see that there's a certain amount of energy associated with each level. Kind of makes sense. And the energy is given in electron volts. The ground state is negative 13.6 electron volts for hydrogen atom. If you get up to here, you get 0 energy. So you're crossing over into the positives. And it also says that at that level, what happens is ionization. We know that ionization means you take an electron away from an atom. So this is what ionization is. You give an electron enough energy to escape its parent atom and leave. That's called ionizing. And in an energy level sense, we think of that as when the electron gets far enough away that you've given it enough energy so that it is no longer bound to that atom. So I've shown you mercury and hydrogen, but there are energy level diagrams for every element and every different element and every different molecule, really. Basically anything you can have an energy level diagram. Each element has specific energy levels, orbits shown by energy level diagrams. Now, so Bohr took it a huge step forward. Okay, Bohr's model with these certain fixed orbits did really, really, really well for hydrogen. Okay, it predicted the hydrogen energy levels almost perfectly. It wasn't very good for predicting energy levels of other elements, but basically, we got hydrogen, we nailed hydrogen with this. We got so close to perfect with predicting how hydrogen was structured that it was kind of realized that, okay, so this theory is really close to right, but there's some other things that we don't quite understand yet. And since Bohr, it's been about 100, 120 years since Bohr and his ideas, we have now come up with our current model for how atoms are structured, which is called the cloud model. This is the best or most current model. Instead of Bohr's fixed orbits, the idea of orbit still exists, but it doesn't have to be exactly in the orbit. Instead, electrons have a probability of being in a certain location. So there's some fuzziness to the orbits. Or another way you can think of it is instead of like these nice, when you see like a little simple diagram of an atom, there's lines that the electrons are all on. Instead of just nice thin concrete lines, we smear the lines out. Okay, so that the lines are a little thicker, and there's a chance of the electron being somewhere along that smudged out or smeared out line. Kind of like a cloud, which is why it's called the cloud model. You if you've flown, when you go up into a cloud, there's not really an edge to a cloud. You very gradually kind of seep into the cloud. Okay, so therefore, an electron isn't really just a particle, since it can be in multiple places at once, or there's a probability of it being in many places. This is a wave property. It's very hard to say, and it's impossible to say, in fact, that a wave is in exactly this spot. Instead, we say that a wave has a probability in being in multiple spots. So that means that the electron is kind of like a wave. And the cloud model ends up predicting atomic structure and atomic properties and phenomenon very, very well. We're going to talk a little bit about atomic spectra before I end this video. Essentially, here are the two energy level diagrams that are in your reference tables. And again, one is for hydrogen, the other is for mercury. Why'd they pick hydrogen and mercury? Well, hydrogen because it's very simple. Mercury, I'm assuming it's fairly simple since they're picking that, and they're only giving you some of the energy levels. The energy level diagrams represent the different amounts of energy, or in other words, the different sort of orbits that an electron can have. And every element has a unique set of these energy levels. So again, here's hydrogen, here's mercury. And like we talked about before, if you want to make an electron move up one energy level, up from one energy level to the next, it must absorb a photon. What this means, if you're absorbing a photon is a particle of light, and light carries energy with it. Photons carry energy, so essentially you're gaining energy. It must absorb a photon in order to increase its energy. Here's one of the most important things, though. If this is going to happen, the atom has to absorb the exact right amount of energy, or nothing will happen. For instance, if you have an electron in the ground state, n equals 1, and you want to send it up to n equals 2, well, the ground state energy is negative 13.6, and the difference between that and negative 3.4 minus negative 3.4 is, well, 10.2 electron volts, which means if you want to send an electron from the ground state up to here, it has to absorb an electron with an exact amount of energy. It has to absorb a photon with exactly 10.2 electron volts, or else nothing will happen. If it's 10.3 electron volts, it won't move. If it's 10.1, nothing. It has to be the exact right distance. You can't have an electron overshoot. Remember, there's certain, Bohr said, and although he's not exactly right, this is pretty much how it works. You have to be, for our purposes, when you absorb an electron, it has to be the exact difference between two energy levels, where you're going and where you came from. Otherwise, nothing will happen. There's no such thing as an electron going almost up to n equals 2, or going just a little bit past n equals 2, but not to n equals 3. It has to be the exact difference between energy levels, and we'll practice that, and we'll see that as we go on. I'm going to stop that there, though.